In this webinar, we're going to look at how Maple can be used to enhance a first course in differential calculus. Now, part of the enhancement will be the use of syntax-free techniques, so that it's the calculus syllabus, not tool, that's being taught. Now, part of the enhancement is the illustration of resequencing of skills and concepts. That's a concept phrase that comes out of the literature, and it means put the development of concept before the development of manipulative skill. Typically in a calculus book, what do you find? You find that emphasis is on skill development first, so that those skills can be used to manipulate and juggle concepts, hopefully leading to the learning of the concept. But what you got when you have a tool like Maple available, you can use Maple to juggle the concept, so that you can emphasize the learning of the concept first. Then you can turn attention to the manipulative skills, illustrate them in Maple, implement them in Maple. When the student sees the big picture concept, where the skills fit in, what those skills necessarily are, the task of mastering the skills is much easier. And I've seen that in my courses in Rose-Hulman that evolved into the optimal way of using Maple in the classroom. Assuming that the derivative has been introduced pictorially, graphically, numerically, the secant line approaching the tangent line, etc., then some calculations where analytically you apply the definition of the derivative as the limit of the difference quotient. So here is a typical problem in which the function is a polynomial. The solution here in Maple starts with the definition of this function. So I'm going to select it, hold down the control key, and pull it down here. I call that a control drag. It's not a Maple thing, it's a Windows thing. I'm in Windows. It can also be done in other operating systems. It's equivalent to copy paste, but it's just fewer keystrokes. Now, I'm going to go here to the context panel and select assign function. That does all the machinery of defining that as a function. Now, here is the limit of the difference quotient. I could drag this thing over and use it, but let me show you how you build something like this. So, in the calculus palette, you will find a limit operator. I have put that into my favorites palette, and the way I put it in there is right click on it. Remember, I got a 2-button mouse, and you have this option, add to favorites. That's how you populate the favorites palette. So I'll be making use of this. So there's the limit operator. H, use the tab key to move through the fields. H is going to 0, and then we want to put in the difference quotient. Well, if we type the letter H and hit the slash key twice, H will go to the denominator, and then we type f of x plus h minus f of x. There's the difference quotient. Limit operator acting on it. What is it worth? Well, if you see up here in the context panel, evaluate and display in line, that means evaluate that limit and put the answer in line with the limit operator. There's a keyboard equivalent. In fact, there are two. Control equal, which is what I always use, and Alt enter. So control equal, I get something. 9x squared minus 11. Well, if we write f of x. Hit the enter key. So we have the rule echoing back. In the context panel, we see differentiate with respect to x. When we do that, we get 9x squared minus 11. So what does that mean? It means this operation called differentiate and this business of limit of the difference quotient, they give the same answer. So let's dig in a little bit more deeply and let's see from first principles what the difference quotient looks like. So I'll begin with the numerator. F of x plus h minus f of x. Hit the enter key. And you look and you see an x plus h cubed, and you realize you've got some algebra to do. So either expand or even simplify will work. Expand, and this binomial to the third power is multiplied out. And then you notice every term has an h in it. So maybe we should hit it with factor. This is the factored form of the numerator. We are going to divide this by h. How can we do that? Well, notice how these blue outputs have equation labels. Those labels can be used to reference the item actually in Maple. You do that with Control L, L for label. You bring up the Insert Label tool, and you put the equation label number. And if I divide that by h, I have now the difference quotient. By the way, if you want to see what that label is pointing to, change label to label of reference. I just right-clicked on it. And then you actually see what you're dividing by h. This is the result. Now, if you're working with a pencil and paper and you've gotten this far, how do you get the limit? Well, what do you try first? You try letting h be 0. If nothing bad happens, then that's the limit. So evaluate at a point. Let's let h be 0 and see if anything bad happens. Well, no, look, you get your 9x squared minus 11. So this process of limit of the difference quotient, which means differentiate, gives you this 9x squared minus 11, and here you've done it stepwise. As a student sees different examples of limit of the difference quotient, what they discover is that different functions take different algebra in order to work out that limit. Unfortunately, they can lose sight of the fact that it's the limit of the difference quotient that we're looking for and not the algebraic details of how to take that limit. So if the function is a square root, you'll find that the algebra that was used for polynomials is not the algebra you used for the square root. So what is the limit of the difference quotient and what is the algebra? We need this function, so I'm just going to type f of x equals, I have a square root template here in my favorites palette. It came from the expression palette. You saw how I put things into my favorites palette. Assign function. Limit of the difference quotient. You saw how I built that in the previous example. Drag that down. Control equal. So if you take the limit of the appropriate difference quotient, you get 1 over 2 root x. Is that the derivative? If you take the derivative of root x, differentiate with respect to x, 1 over 2 root x. Okay? Now let's examine the algebra more carefully. Here is the difference quotient. I'm just going to drag that down. If you immediately try to set h equal to 0, you will have here root x minus root x, which is 0. And the 0 in the denominator, that's an indeterminate form. You've got to do something. Well, the secret trick is rationalize the numerator. Maple does not have a rationalized numerator. It has a rationalized denominator. So let's make the numerator become the denominator. by taking the reciprocal. So 1 over control L3, then take the then rationalize that. Then you have to flip it back. So you need 1 over control L5. That's the algebra that you needed to employ. You can set h equal to 0. I get it a point, h equals 0. And you get the 1 over 2 root x. After differentiation has been mastered, then it's applied. And one of the applications of the derivative is in unconstrained optimization. So here is a problem in unconstrained optimization. What's the point on this curve that's closest to this point? Here's a visualization that helps understand what it is that we're trying to do. This is a graph of the function. This is the fixed point. The green line connects a point on the graph with the fixed point. As I move this slider, the distance or the length of this green line is written here, and the x-coordinate is written here. So the slider is controlling the x-coordinate of the point on the line, and we're trying to make this number as small as we can. So 162, that looks like, with this pixel count, it looks like 16, I can hold my hand steady. My hand moves when I take the finger off the button. There, got it. Okay, that's the smallest we can get using this pixel count. And it also shows that the green line seems to be perpendicular to the curve. So there's a visualization that a student can play with and say, oh yeah, this is what we're trying to do. We're trying to make this green line as small as possible. Distance between this point fixed and a point on the curve small as possible. Let's solve this problem. Begin by thinking about defining the function f. But there's a caution here about the exponential e. The e that I've typed here is a script e. It is not the exponential e. I'll give you two different ways of getting the exponential e. You can take it from one of the palettes. Now, if you go down here to common symbols, you'll see an exponential e. And if you hover over it, you'll see it says exp of 1 is the exponential e. You get it into the favorites palette. So you can type or click that, and you have an exponential e. It is not enough to type in e, select it, and make it bold, because that appears to be bold Roman. That's not enough. That doesn't do it. You have to either get it from the palette or type in E and then use, let's take this bold off here. Type in E and use command completion. Now, the easiest way to do command completion is to press escape. A table comes up containing all of the things that start with E, and the very first one is the exponential E. So those are your two choices for implementing the exponential E. To do the calculus part of this problem, we'll begin with loading the Student Calculus 1 package. So Tools, Load Package, Student Calculus 1. Maple has over 100 packages. All it means is the library code is bundled into these nice, neat little clumps. It's all part of Maple. I'm going to drag this expression down, f of x equals. But before I make it a function, I'm going to select this e, which I typed as just the letter E, and I'll click on the E in my favorites palette to make that E the exponential E, and now I can assign function. Okay, what is the distance going to be? Well, it's between fixed point 1, 7, and notice points in Maple are represented as lists of square brackets, and a point on the curve, which is f comma f of x. So, what is the distance between these 2 points? Well, if we go to Student Calculus 1, the only thing that Maple sees that makes sense here is to get the distance between them. And I want to make that expression, which I'm going to minimize, into the function d of x. And I want to reference this. I don't want to retype it. Use Control L2. Now I can do assign function, and I have this function d of x. Well, d of x is that function. I would like to draw its graph, so I can use this context panel, plots, plot builder. Now I'm drawing a 2D plot, so I click here, and I notice that the default is minus 10 to 10. And that gives me these great big numbers because you have hyperbolic sine and you have exponential. Let's change the domain. Well, this one should be 0. Left boundary should be 0. And from what we saw in the animation, 4 should be enough over here. And we see that we have a function that appears to have a minimum. But Maple has cut off the bottom part from 0 to about 2. Let's tell Maple to give us a better view. Let's have it give us the view from 0 to about 7. I could put a 7 in here. 7, right? Okay, so it's a much nicer image of where this minimum is. It's somewhere between 2 and 3. Well, how do you minimize? You can do it numerically. D of x context panel, optimization, minimize, you get a local minimization. This is the shortest distance, and this is the x for which that's the shortest distance. Or we can do it analytically. Take the derivative, d prime. Now you can use an apostrophe. I like to use this prime symbol that I get from the punctuation palette. See, there's a prime, double, triple, even a quadruple prime. I just think it looks nicer than an apostrophe. So there's the derivative. Now, you want to set this equal to 0. Well, we could have put the 0 equals 0 here. Let's just redo that. Either way, Maple solve command doesn't mind. You're not going to get an analytic solution out of that. You have to solve numerically. So go here to solve. If you say numerically solve, you don't know where Maple will start the Newton iteration that it's going to use from. So tell Maple where to start it. We know it's the 0 is going to be between 2 and 3. There is the x value. It agrees with what we got numerically. And what might you want to know now? You might want to know the value of that distance. So d of, well, use the equation label to reference the x. That is the shortest distance. If you want to know the y coordinate, you need f of that number, that x, Control L7, and the y coordinate is 6.76. And if we go back up here to our visualization, the y coordinate is close to 7, and the best distance that we could get was 1.62 at 2.6. That pixel count doesn't quite get you the accuracy that you see here, but it gave us a ballpark and an understanding of what we were trying to do. Another application of the derivative is found in Newton's method for solving equations. So here is a problem to solve by Newton's method, and what we'll see is how the idea of Newton's method is implemented in that formula that one applies when they're doing Newton's method. There is a tutor that we can make use of. Now, what are the tutors? You go ahead to Tools, Tutors, 50 some odd pop-up tools that allow you to experiment and solve problems in a point-and-click, syntax-free manner. So if you go here to single variable calculus, you will see down here a tutor, Newton's method. So that's the one we're going to use, but I'm going to get at it through the context panel. I want to load the Student Calculus 1 package, so Tools, Load Package, Student Calculus 1. We need this expression. I didn't want to put it there. I want to put it here. We go to the context panel, Student Calculus 1, Tutors, Newton's method. Okay, so here we see a pop-up. The function, the rule for the function is here. An initial point has been chosen. Our instructions here say start at 1.5. Display. So what do you see? You see the iterates. If you go more than the default 5, let's do 7. Maple quits at 5, which means the 6th one is going to be the same as the 5th one. What Maple is trying to draw here are the tangent lines that determine the iterates. And down here what you see is Newton's method as a command. So there is a command that you can use to apply Newton's method. I guess if we click close, you will get that graph written. What that graph is telling you is if you start at 1.5 and you go up to the curve and draw a tangent line at that point on the curve, look at where the tangent line hits the x-axis, so the x-intercept of that tangent line. At that point, go back to the curve, draw another tangent line. The x-intercept of that tangent line is the next iterate. Go down to the curve, draw a tangent line. The x-intercept of that tangent line is the next iterate. So that's how you get the Newton iterates. From first principles, we want to write x minus f over f prime and see what happens. So we begin by defining this function, a sine function. Then we want to write x minus f of x over f prime of x. What does that look like? This is the expression we want to make into the iteration function. G of x equals, let's use the equation label for that, and a sine function. Okay, the iterations start at 1.5. So what is g of 1.5? It's that number. We want to apply g to that next. So g of control L2, apply g to that, g of control L3, g of control L4, g of control L5, g of control L6. Those two numbers are the same. These last two are the same. So that's as far as we can get in accuracy using this many digits. But let's look at the geometry behind what this formula is doing. That's what I mean by implementation of the theory. Okay, so we've already defined the function f of x. The rule is that, and we want a series expansion. So we go to, here it is, series in x. We want to make a series expansion around 1.5, which is our initial point. And by taking the order 2 and removing the order term, we have essentially the tangent line. Now, we want to solve for x, because this is being set equal to 0, and we want to solve this for x. Numerically solve will do. That gives us the first iterate. Now, we want to do this same process again, with this being the expansion point, because we want the tangent line at that point. So f of x, series in x, expansion point, second order, no order term. Solve this for x, and that's the second iterate. And we'll try that one more time. F of x, series expansion, because this is what we're using to get the tangent line. Series in x. I didn't copy and paste. I need to copy this so that I can paste it here when I do series. Paste it here. This is a 2. Check this box. And then solve for x. and that's the third iterate. 1.895, 1.895, and so forth. So what we're really doing is exactly what the tutor showed. Tangent line, find the x-intercept on that tangent line, use that as the next approximation to the root. Another application of differentiation appears in constrained optimization. Here's a pretty standard problem in constrained optimization. Find the largest rectangle that can be described in the upper half of this ellipse, and it goes without saying that the sides of the rectangle are parallel to the coordinate axes. So there is the ellipse, and we want to start with a picture. Here's the picture. We have the upper half of the ellipse. This is an animation. I'll do it this way. What the animation shows is a rectangle in red. The upper corner indicates the area of this rectangle. The x-coordinate of the right edge is written up here. If we look for the largest area, we see 7, 4, 4, 2, then the numbers get smaller, 7, 4, 6, and then it goes down again. So 7, oh, I can't keep my, well, maybe I can do it this way. Yes, 7, 4, 6, oh, it's the best maximal area that I can find. But what this shows is, how do you find the area? This distance is x, this distance is 2x, and the height is determined by the y-coordinate on the upper branch of this ellipse. In a sense, we've just gotten a graphical solution to the problem. We can get a numeric solution to the problem. We need a sequence of the objective function, which is 2x, and then a space for implied multiplication with the y. The constraint equation, I'm just going to control drag that down. If I go here to optimization in the context panel and look for a local maximization, I get an x-coordinate, 2.449. Well, that's about as close as we can get on this pixel count. Maximal area, 7.7459. Well, that 746 is close. And this is the y-coordinate on the ellipse. And now a solution from first principles, the kind of computation that you would expect in a calculus course. Well, we need to solve for either x or y in the constraint equation, because this is a calculus of a single variable. So let's grab this constraint equation, drag it down, and let's solve for y. There are two branches. We want this first branch. The area function will be 2x space, and I'll just drag this stuff down. That's the y. And I want to make this a function. what do? You take the derivative and set it equal to 0. So a prime of x equals 0. That's the equation to solve. Now, if you were working by hand, you'd probably want to simplify this. Maybe we could just hit it with solve, but let's do the simplify. Simplify, simplest, simplify. And you can see that the solution is going to be plus or minus the square root of 6. So solve will tell us it's plus or minus the square root of 6. Well, we're in the upper part of the ellipse, so square root of 6. We could, let's take that, select element 2, let's float that, approximate that 10 digits. Okay, 2.449, which is consistent with what we did numerically. Now, the expression that gives us y is this positive branch on the ellipse. If we evaluate that at the point, and I'll just type in SQRT of 6, we have this number. You could probably simplify that. In fact, simplify. Maple takes out the 9. And if you want to float that, you could float that 1 point. That's the height, 1.58. Here we did it numerically, 1.58. And the x was 2.449, 2.449. So we were able to tackle this problem graphically, numerically, and analytically. Another application of derivatives in Calculus 1, first calculus course, Differential Calculus, related rates. Now, related rates are simply an illustration of the chain rule. But related rate problems take on a life of their own because students who do not have problem-solving skills, the ability to analyze a problem, extract what's given, extract what they want to calculate, visualize how to get from what's given to what they want to end up with, those students see this stuff as intractable. And that's a shame because it's just an application of the idea of the chain rule. So here is such a problem, the sand pile problem. Sand pours from a hopper at a steady rate. That immediately tells you something. It forms a conical pile whose height is observed to remain twice the radius of the base of the cone. An observation is now made. When the height of the pile is seen to be 20 feet, the radius of the base seems to be increasing at the rate of a foot every 2 minutes. How fast is the sand pouring from the hopper? By way of solution here, we need to analyze what we are given and what we are to find. And this picture is helpful. This is a cross-section of the cone taken through the axis of the cone. The height is twice the radius. So we can write down h is 2r. Sand pile forms a cone. Volume of a cone is pi over 3 r squared h. But h is 2r. We know that at the moment when the height is 20, that is when the radius is 10, radius the base, r dot, and the rate of change of r, is a half. What we want to find is V dot, the rate of change of volume, which is a constant. Begin, write the volume in terms of just R. So it's pi over 3. You have an R squared. You're going to pick up an R here. So you need a 2. So let's stick a 2 here. And then you need an R cubed, but you need explicit dependence on t. This is the expression for the volume. Its rate of change, that's a derivative with respect to t. You want to evaluate this when R is 10 and dr dt is a half. Here's a way to make the evaluation. Use this task palette template. It's the evaluation template. It comes out of the expression palette. Keep it in my favorites. I'm evaluating this expression, so it has a equation label, Control L2. Down here, I want R of t to be 10, and I want R dot of t to be a half. Now, I'm going to make R dot, and I'll explain to you how I did that, equals 1/2, 100 pi. And just to clarify, any symbol you can be jumped up on top of. So here's the R by the following 3 keystrokes: Control, Shift, and the quote key. That will put you on top of anything. Period for that derivative with respect to t, and then you just type of t. When I taught anti-differentiation, I wanted to teach it without having to mention integration. Now, there is only one place in Maple where you can obtain an antiderivative without having to invoke an integration command. And so let's look at this problem. Find all antiderivatives of x squared. Do it at the beginning of the discussion where you want to get antiderivatives without having to jump the gun and say int in Maple. Well, here's how you can do it. Load the Student Calculus 1 package, Tools, Load Package, Student Calculus 1. The expression for f of x here, this is simply x squared. Now go to the context panel, Student Calculus 1, Tutors, Antiderivatives. So it's Antiderivatives Tutor. Okay. This takes x squared and graphs it. You see it's the one in red. It also graphs an antiderivative. This is the antiderivative it graphs. It picks the one that vanishes at the leftmost endpoint. See, that's what's done here. And the picture is drawn by this antiderivative plot. Now, if you say show the class, then you get a family of antiderivatives. And if you uncheck this and change the domain to 0 to 1, then this is the function. This is its derivative. So the general one is this function plus a constant of integration, arbitrary constant. But this is the only place in Maple where you can get an antiderivative without having to mention the word integrate. Another application of derivatives is in computing curvature of a plane curve. So here's a problem where we're going to compute the curvature of an ellipse. This is the ellipse. And to make it a little bit more interesting, I ask for where and what is the maximum and minimum values of that curvature. By way of solution, why don't we graph this ellipse? So grab the equation, drag it down, go to plots, 2D implicit plot, variables in the order xy. It looks like we've drawn a circle, but we need to do constrained scaling. Now we can right click on the graph and select constrained scaling from here, or we can use the context panel and do it from the context panel. Looking at the graph, it would appear that the semi-major axis is 5 and the semi-minor axis is 2. Now, I want to pick a branch because this is one branch and this is the other branch. And that brings us back to this formula for curvature. In modern books, modern calculus books, curvature is taken as positive, but y double prime has absolute values on it. I had my hands on, for many years, an old calculus book, might have gone back to 1927, Granville, Longley, and Smith. Way back then, they did not put absolute values on y double prime, and that meant you got one more piece of information. If since y double prime gives you the concavity, if the curvature is positive, graph is concave up. If it's negative, it's concave down. So if we pick the bottom branch where concavity is positive, then y double prime will be positive and I won't need to mess with absolute values. So when I solve this equation for y, I'll have two branches and I now know which branch I want to pick. So let's go here to solve, obtain solutions for y. There are these two branches. I want to pick the negative one because that's the one that sits down here, but it's concave up. So I can get my hands on that by select element 2. It's the second one in that series. So now I want to write g of x equals this stuff. So let me put it here. And make a function. I've rewritten the curvature in terms of g without absolute values. So let me grab this, drag it down, press the enter key. There's the curvature. It's clearly in need of a simplification. So I go here to simplify, a variety of ways to simplify. And now I inspect and I see I'm going to want 25 minus x squared to stay positive. So I really want x to be between minus 5 and 5. So I'm going to simplify, assuming real range. So I want x to be in the interval -5 to 5. But I want that interval to be open because I don't want x to equal either -5 or 5, because then I'm going to have zeros in denominators. And you can see here, this is a copy of this dialog. So this is a simplified form of the curvature. Remember the questions that I asked. Where is this maximum? Where is this minimum? If we go up here to the graph, we can guess from the graph that the curvature is a maximum out here at 5, turns most rapidly, and it seems that the minimum of the curvature should be down here at x equals 0, where it's not turning quite as fast. So let's graph the curvature. Simplest way to be dealing with that would be to give this a name, kappa, and then we can reference kappa more easily and draw its graph. So plots, 2D plot. Well, the default domain is -10 to 10, but out here and over here, Maple didn't find any real values, so it drew the graph on -6 to 6. And you can see that there is a minimum to this curvature at x equals 0. Where's the maximum? Well, it's got to be up here at the end point, which is probably x equals 5. Now, if you want to get the maximum in analytically by calculus, there's kappa, and you want to take its derivative and set it equal to 0, so differentiate with respect to x. Set that equal to 0. Well, Maple's solve command doesn't mind that you don't set it equal to 0. It will assume that's what you meant. Solve. And you only get the x equals 0, because that is the only point where there's a horizontal tangent. The other extreme value is up there at 5. So this is the curvature. If I can keep my fingers, I'm telling my fingers to do the right thing here. There's the curvature. I want to evaluate that at x equals 5. So that's the maximum curvature, and it certainly will yield to a simplify. That's the maximum curvature. What is the minimum curvature? Well, the minimum curvature occurs at x equals 0. So let's do a substitute into over here. Let's substitute into kappa. Again, root 625, that's 25, so a simplify will do well there. So there is the minimum value of the curvature. It occurs at x equals 0. Maximum value of the curvature is this 5/4, and it occurs at either plus or minus 5.